Okay, so I'd like to, I'll go over these. I think that would be beneficial. I mean, rather than letting you aimlessly wander about. Yeah, would it serve you well to just kind of go through these? Okay, so let's see if we can do them all. We'll slow down only if we need to. Okay. All right. So by the way, one small typo correction on number 1 there. That's supposed to be an equal sign there in between. The asymptote of G is, well, first of all, why does it make sense to even ask about G? Why can't you even ask about F? What's going on? What are these two graphs? What's going on there? F is, and G is something exponential, and if it's got an exponential behavior, then you know there's going to be an asymptote somewhere. So it is worth asking this question about G, and the answer is what? Think about transformations. What's the normal asymptote? What's its normal equation for an exponential? If we just had like the equation y equals a to the x, or b to the x, or whatever, what's the normal horizontal asymptote? Yeah, y, and let's always say y equals 0, right? But of course, what's happened here? There are kind of two actions that have happened to this graph. Can you name them? What's the plus 1 do? Start with that. It's been a while, huh? Anybody? For any function, replacing x by x plus 1 results in a nobody. It's still early. Muhammad, help us out.
Translate 1 unit
to the left 1 unit, yeah. And then the minus 2, somebody different? What's that do? In terms of transformations? Yeah, John?
Sorry.
Yeah.
Can you shoot me that thing?
What?
That list of jumps.
Oh, yeah. Yeah, no problem. Yeah, down 2. Okay. All right, where were we? So if we're moving down 2, then instead of y equals 0, it'll be y equals -2. Yes? The domain and range of f. Let's start with f. Now, I would probably have to, for the domain, I think for both of these, we can maybe just start by saying it. What's the domain of those? Yeah, is there anything that we're restricted from putting in for x? I think we can take all real numbers as the domain for either one of these. There's no x value that's disallowed. The range is a little trickier to think about. I might benefit from thinking visually on this. You might have other ways of thinking through it as well. But I would really, for this one, for example, for f, what's the range of f? I really want to picture what f looks like. Can you already in your mind? It's x squared, except, again, I want to think transformations here. What's the negative x squared look like? That's just this. And then plus 4 means moves up 4. So I already have this picture in my mind. You can draw it if you like to. So what's the range? What's the lowest y can be first? Negative infinity. It's going as low as you like, all the way up to, but not exceeding 4. Yeah. Good. And then the domain and range of G, remember we just talked about the transformations associated with this graph. It's just 2 to the x, which I think you're comfortable looking at. 2 to the x, there it is. But we said left 1. Well, that doesn't really affect the range at all, but whatever. Okay. And then down 2. So what's the range? The lowest y can be is -2. I'm using a parenthesis to emphasize that it can't be -2, but it can be as arbitrarily close to -2 as you like, provided you pick the right x value. And y can be, as you know, as large as you like. Very quickly it becomes as large as you like. How do we describe the end behavior of f? Again, picture this, if you like, and also pull on our discussion of end behavior that we've been having recently. So we want to describe 2 statements here, right? As x approaches -infinity, f of x approaches, and then you'll tell me here in a second, and as x approaches infinity, f of x approaches what? So this first statement describes the left end behavior, and the second statement describes the right end behavior. And so what are those 2 blanks for this graph? Keeping in mind the picture that you just drew in the air, Ethan. Yeah, in this case, they're both -infinity. Good, let's keep going here, keep rolling. What about G? not a polynomial. So the answer is, it doesn't necessarily look like the things we've been talking about recently, but we can still have this meaningful discussion about end behavior. What happens, we've already thought about the way this looks, so what happens as x, I guess we'll start with negative infinity. As x goes to the left, what does f of x approach? Anybody? What'd you say? G, sorry, whatever. Yeah, go ahead, Maya. Here, I'll write that properly there. Yeah, so as x goes toward negative infinity, what did we say the graph looks like? How does this work? As you plug in a number like negative 1 million, what are you getting? Something really close to what? Yeah, -2. And on the right, looks like that, we said, right? So what do we say there? Oh, a positive infinity. So that describes the left and the right end behavior of that graph. The y-intercept of f, remember, the y-intercept for any function you ever meet in your whole life can be gotten by just plugging in 0. So what's f of 0? All this is asking? 4. And for g, 0, if you plug that in, you get, actually, yeah, 0 there, right? I guess this graph goes through the origin. That's interesting. And then the x-intercept of f, or maybe I should say x-intercepts. That is, when is negative x squared plus 4 equal to 0? Can you figure out when those are? That's not as easy to say. You can either think visually about this if you have a really good graph in your mind, or you could actually think about this and solve this equation. You know how to solve that equation? I think you do. There are a couple ways you could do it. You could factor it, or you could just move the x squared over. What do we get? When is f of x 0? Yeah. Yeah. Don't forget, we need both. Yeah, so at x equals, so we have the point -2, 0, and also the point 2, 0 on that graph. All right, and then we're supposed to graph these. We should have maybe started with this, right? 1, 2, 3, 4. And there are the 2 points Rasmus just named. Something like that, right? And over here, we said asymptote. Let's graph that clearly and label it. And we already said 1 point there. And I think you'll find you get that kind of behavior. So, how do we do? Okay, that's the kind of detail I'd like. I'd like to be able to look at the graph and at least tell a couple of points from it clearly. And if it's not clear, then you should label them. But I think it's pretty clear what points I'm indicating in these pictures. Yes? Okay. Let's talk about number 2. I think I'm going to need my calculator for this, so let me pull this out here. So we got a bacterial growth model. B, in terms of T, where T is the number of hours, so T is measured in hours since noon. Okay. Where's my calculator? There it is. Okay. So actually, maybe I'll put this in, what is this? How many hours will it take for there to be 120,000 bacteria? Okay. So I'll throw this into Y1 here, just for fun. Come on now. Not necessarily because I want to be able to see it, but just because I might want to evaluate it. Did I get that typed in right? I think so. All right. So you could actually, on the home screen, you could actually type this in, 15,000, and you know there's an E for you to set the blue second button, and then ln. You get E to the, so you could actually type this in just how it is there. You can also do, now I hesitate to do this because all of you have different calculators out there, but there, on all of your calculators you can get a Y1 on your menu. And then if you want to know what it is at 5 p.m., it's since noon, right? So that corresponds to t equals 5, right? Did you get that, people out there? Did you do A and get this answer? 57,861.38. You want me to actually type it in?
What's the exponent?
0.2, isn't that a 0.27 on your paper too?
Times 5.
Yeah, times 5, because I think t is, it's 5 o'clock, which, and we're measuring t in hours since noon, and 5 o'clock would be, then be 5 p.m. would be 5 hours since noon. So that's convenient, the way we have it set up. Great, so 57861. Let's see if I can remember that. 57, what was it? I guess I still have it here. 861,383. So let's say to the nearest whole number, 57861, I guess. Okay. How many hours will it take for there to be 120,000 bacteria? There are 2 ways you could actually. I think we taught you 3 different ways to do this. One way to do it would be to like make some guesses along the way. In the end, I hope you understand that this is the equation we're trying to solve, right? Right? And asking what's t that would make this true? So some of you might have started by dividing by 15,000, which is a great move. But then maybe some of you got stuck in that place. Then you're like, okay, well, what do I do next? How do I undo that e? And so we'll have to discuss how to do that in a second here. Certainly, one way to solve any equation at all, this is such a robust technique that it always works, is to actually graph this, right? So if I graph 1, 2, 0, 0, 0, 0, is that what it is? Yeah, 4 zeros there. Okay. Now, graphing this is going to be a little tricky because obviously those are some big numbers, but that's okay. Let's graph this. Let's make sure we capture x up to, maybe we see like 12 hours of behavior, you know, and if we need more or less, that'd be fine. And then I'm certainly going to need y to go up to 120,000 at least, right? So, I don't know, let's do 150,000 just for fun. Let's take a look at the growth model coming up down below and the constant function, 120,000. And already you can see where the graph achieves a y value of 120,000, right? It's whatever x value this is. It looks like 1, 2, 3, 4, 5, 6, 7, 8 or so, right? Of course, that's not precise, so let's use the calculator's intersect feature. Number 5. First curve asks, second curve, yay, guess. Where it doesn't really matter, it'll get it. There's only one place to intersect. So 7.7016, approximately 7.702. How many hours? Correct to 3 decimal places. All right, so there's one way to get the answer, which would be fine. You're welcome to use the calculator. Let me just show you how you might do it algebraically without doing it visually. I think we all would want to maybe start by doing 120,000 divided by 15,000. Like I said, conveniently, that's just 8. Okay, great. But then, what do you do next? Help me out. Does anyone have a next algebraic step that can get us in the direction we need to go here? How do we do, what's the inverse of e to the? Yeah.
Cross out e ln to the 8.
Yeah, you remember, if we're asking, boy, gee, wouldn't I really like to know what power e needs to be raised to get 8? Isn't that the question you're asking yourself? Like, what is this power that I would have to raise e to get 8? And that question is exactly the question that a logarithm answers. And in particular, we need a log base e. And we usually just write that as ln 8. So I think we have our answer then. T is approximately equal to, well, I shouldn't say that. T is exactly equal to ln 8 divided by 0.27. And then now if you want to approximate that, you can. Let's actually type that in. ln of 8 divided by 0.27. So actually, only doing this one step and getting 8 and then typing this in, you might actually prefer that to the graphical method, which takes you figuring out what the window is and then using the intersection feature, and it's a little more time consuming, and I don't know. So whichever though, both options are available for you. The third technique you really could use if you wanted is to use like that whole like squeeze technique, and actually like narrow it down by making some progressively better guesses, right? So you have a couple different options for how to solve an equation of this kind right here. I think that answers that question. And does it answer? I heard at least 2 or maybe even 3 people who are like, "Can we go over number 2?" Is that good? Does that satisfy the hunger in your hearts? People who ask me about number 2. Whenever you are. Yes. Okay. All right. All right. More exponential equations. Let's do this. I think it's pretty clear that on this first one we're going to divide by 5 first. See if we do this calculator. Will that be 275, right? Times 2, which is 550? Okay. And then, again, this is a nice one to use for progressive approximations. This is definitely something that's greater than 2, right? And less than 3. So I already know the answer is going to be to you, that it's going to be 2 point something. I'm feeling like probably 2 point, I love making a guess. What do you think? 2.3 maybe? 2. Well, you already know. It's more fun. Okay, but I'm thinking it's on the. I mean, it's not very close to 1,000. 2.4 maybe? 2.5 at the most, maybe 2.5. What do you think? I don't know. Let's give it a try. How do we do that? What's the question we need to answer here? It's just like the last one, except this time, yeah, it's a log base 10 of 550, or we often just write log 550 since we call that like the common log, right? And that's in fact the log button on your calculator. It doesn't have a base label on your calculator, so it's using the same assumption that that's a log base 10. So we can write down what that approximately equals to. Log 550, 2.7. I was totally wrong. 2.740. Go back to school, Mr. Chase. Okay. What does it say? Also 3 places. Okay. So I guess that's good. 3 decimal places. That's the closest. Okay. We just did one like this a second ago. That'll be, what are we looking for there? How do we, yeah, ln 142. Again, both of these could be solved by graphing as well, right? You could plot the left and plot the right side and find the intersection, and you have an agreeing answer that agrees. Okay, so ln 142 divided by 2 is our exact answer. That's perfect. That's absolutely perfect. But we can also give a rounded answer here. It's 2.478. 2.478. Oh, we should have made an estimate on that one too before we started. We could have figured out, I could have thought, okay, well, what's 3 to what power gives you 142? E is almost E. So far, so good? Hit the pause button anytime you need to. Okay, let's do what Jack would have done and solve this symbolically. So I might start by, if I was Jack, squaring both sides to get rid of the square root. It's already conveniently in that form, so. Careful when you're squaring the x plus 1. I'd move everything over and collect terms on one side. This is convenient. That 2x goes away. And I already solved this equation today with Rasmus. You get x equals plus or minus 2, right? of course. Now, it does say, like it says here, that we need to check for extraneous solutions, so that means going back and plugging them in. Now I can already tell that -2 is a problem. Can you? If you plug in -2, on the right side we get -1, and a square root only outputs positive values. So already I can just tell you right now that x equals 2 is the only solution. X equals -2 is extraneous. Which, by the way, remember means is a solution that arises from legal algebra, right? Forward inferences, and yet does not actually satisfy the original equation. Okay, let's see how Sally does it. How does Sally determine the solution to the equation using the graph? This is very similar to what we were just talking about, right? You plot in y1, one of these guys, the left-hand side, and then the other, in y2, you plot the right-hand side of the equation maybe. And that's what we're looking at right now. You could do this on your calculator as well. And that's the picture she sees. So she does kind of like what we did with the bacterial growth model a minute ago. She's like, okay, I need to find the intersection. And it's not very hard to see what that is on this graph. You don't need like the intersect feature to figure this one out. It looks like, though a graph shouldn't maybe be the whole story, you might want to plug it in and just verify. But it appears to be true that we have the point 23 as the intersection. Now how do you know what the solution is? Is it 2 or is it 3? I mean, I think it's the intersection, but help me remember what our reasoning is around that. What does the 2 and the 3 mean in terms of the significance of this problem? Okay, David.
It means x, when x does x equals 2, and you plug in 2, you get 3, which is the y value.
Yeah, and how does that relate to solving the original equation? What's the solution then? Yeah, so the original equation, if you plug 2 into the left side and you plug 2 into the right side, in both cases you'll get 3. So that 2 though is the solution. Is that clear? Hopefully you understand why even finding the intersection makes sense in any of these situations, like the bacterial growth model. So how does Sally determine the solution of the graph? You can say something about she finds the intersection and finds that it's x equals 2. Please say more, but you know the thing we just talked about. You write something about that. Since they only obtain one solution for the graph, she thinks there should be an extraneous solution. Doesn't know how to show. There are a couple ways you could show how to get the extraneous solution, but the bottom line is obviously that like that's the only intersection, and any other claimed solution that you might have is not a solution, right? I mean that's the bottom line. Is it's the only place this intersects. Now, if you wanted to kind of reconcile Jack's work with this, you might be like, okay, when Jack squared both sides, he made the assumption that like, you know, either one of these, when you square these, notice that if this was the equation, if this was the equation, then you would get that. You'd get the same result when you square it, wouldn't you? As if you square this on both sides, like that negative and positive. In both cases, when squared, gives you the same result. So why is he getting this other solution? What is the graph of this? Well, it looks something like this, right? Right? So you can see that if you make that assumption and square both sides, if you square this and square this, then you're looking at a new system of two equations that has two intersections, not one. Right? And the other solution you can see is x equals -2, and that's how Jack got his. You might think, okay, well, wait, Mr. Chase, couldn't you have also made the mistake of, like, what if this was true? Right? That if you square both sides of that, you also get the same result, don't you? So that would be a great way to show this as well. And there are actually other ways, too, but, well, how do I erase this one? Erase. How would that look? Well, that would be you finding this, right? -1. And you can see you get x equals -2 there as well, don't you? Right? So there are a couple ways you could maybe have thought about this system, why she's not getting the extraneous solution that Jack got, but we can see how Jack got to that solution too. All right, let's just bullet through these. The graph of the function has a horizontal asymptote of y equals 0. How about, what are these called? F? Yeah, it says there. Let me draw a little bigger so we can see. All right, so F and H, right? Both have horizontal asymptotes of y equals 0. You can just see on the graph. The function has a range of all reals. F and H do not. We just kind of mentioned a second ago that they have like a lower bound. Both of them do. But G and P are logarithmic functions. Those have a range of all reals. So I'll write that. The function is increasing on its entire domain. That looks like F to me. Any other ones? Maybe G also, right? Looks like as you walk from left to right that you're going uphill on both of those two functions. Y-intercept at the point 0, 1. Well, that's as easy as just looking at it and seeing. 0, 1, 0, 1. I don't have the equations very easily seen there, but I think if you plug in 0, 0, 1, in both cases you, F and H, do that. The domain of the function is the positive real numbers. G and P looks like have only positive domains. You can't plug in a negative number to those. The graph of the function has a vertical asymptote at x equals 0. That's G and P. Those two, part E and part F, are definitely related, obviously. The function has a domain of all reals, F and H, right? The function is decreasing on its entire domain. Where are we going downhill? Looks like on H. And also on P. I. The graph of the function has an x-intercept at the point 1, 0. G and P both, right? And then the last one, the range of the function is the positive reals, F and H. Yes? I know there's someone who, at least one person who, as I was walking around, said, can we go over that? Does that feel good? Is that good? Satisfy us on. It's been a while since we did exponential and log functions and their graphs, but good. Quadratics. This is good. We've just spent most of our period, and we have is that clock dead?
Yeah.
I was like looking up there as if it was helpful. It's not helpful. 8:18.
Can you go over the number question?
Yeah, sure. So hopefully we have about 12 more minutes, but we have we're going over the part that's most distant to you right now in the past. We've done a bunch of exponential and log stuff, so this will only take a second, so I'll do this one quick. We have a real coefficiented polynomial. In this case, it's just a quadratic. And so we know that if it has one non-real solution, then it will have another one too. We can actually, is that one on here? Yeah, 3 minus 2i is also a solution. If anything is called a zero of a polynomial, then you know x minus that thing is a factor, right? And this is, again, I'm using the language now because we've been studying polynomials recently. Of polynomials, we know this is in general true of any polynomial, but it was true about quadratics when we were doing it too, wasn't it? If something is a zero, well then that thing, it must be true that x minus that thing is a factor. So I think that, if I can even check it, there we go, is another statement I'd like to check. 3 plus 2i is a 0. I think that's what we mean by a solution to this equation. We mean that if you plug it into this function, 3 plus 2i in for x, you get 0. You can check. The other solution is a real number. I think that you can't possibly both check this box and this box, can you? If you know the other solution already is 3 plus 2i. And I think we're all convinced. I think actually this was supposed to say 3 minus 2i. Oh well, whatever. Does it say that somewhere? Oh no, here we go. Sorry. 3 minus 2i is the other 0. Sorry, I was looking at the wrong box. But then this last one is equivalent to that. I think they're all right. You can multiply it out and see, right? Okay. Check all that apply. Yes, please. All right. All right. Well, we'll jump to 13 for the sake of Delia because she asked. So. And by the way, oh yeah, sorry, I shouldn't have said. We should have, if a problem like this is given on the test, then the following formula will also be provided. Okay, so I know it's been a while since you did Newton's law of cooling, so it's the I guess we'll say it this way. It's T, the initial temperature, T0, minus the ambient temperature, times e to the negative kt plus Ta, where Ta is the ambient temperature. But that formula will be provided on the test. So why does that make sense? Well, because if you have a pizza that's heated to, for example, 400 degrees, taken out of an oven, placed in a 75-degree room, then what does that mean? Well, that means that this coefficient out here will be 400 degrees. That's the temperature, the initial temperature of the thing, or the object, or whatever. It's 400 degrees, minus 75 degrees. So this coefficient out here in the front with the parentheses, that represents like the temperature differential, right, between the thing and the room, or the ambient space, whatever it is. Maybe you're putting a popsicle in a refrigerator or something. Well, then it's the ambient temperature of the refrigerator or something, or the freezer.
So is T of A 400 or?
TA is the ambient temperature, so that's what A means, the room's temperature, something like that. So the difference here would be 400 minus 75 here in parentheses. So what is that? 325 is the temperature difference. E to the negative KT. We don't really know what K is. Oh, yes, we do. They gave it to us. Sometimes we make you solve for that, don't we? But I guess that was nice of us. Okay. 0.324 T and plus 75. And again, why does this make sense in terms of the actual physicality of the model? 325, like, first of all, if you plug in 0, do you get an answer that makes sense? What do you get when you plug in 0? Don't you get 400? Plug it in carefully. If you plug in 0, don't you get 400? And why does that make sense from the context? Because that was what we claimed that what was happening, is that T equals 0, the temperature was 400. So that seems to be making sense. And then what's the shape of this graph? What's its horizontal asymptote? Did you know there was one? I don't know, maybe you didn't know that. But there's a horizontal asymptote of this graph. What's its equation?
75.
It's 75, yeah, and by the way, I guess we just answered this question, right? It approaches whatever the ambient temperature is. Doesn't that make sense that over time that the pizza would get closer and closer to the temperature of the room? Yeah. I mean, I think you could if someone, the way that would have to happen is if we just didn't tell you K, then the thing we have to tell you is a sample, T time, and T temperature value, right? And then you plug those two things in, and the only unknown would be K, right? We did do that in class a bunch. I was just thinking that would happen here, but it didn't. Yeah, and so as time goes on, this negative K value up here ensures that what happens, right? We start at 0, 400, and then here's Y equals 75 down below, and then that negative K value makes sure that this looks like that, right? Which is exactly what's happening. So that I just want to make sure this kind of checks out with your like visual, with your like real world context. All of it makes sense. Okay. At what time is the temperature of the pizza 150 and therefore safe to eat? I don't know. Solve this equation and tell me. Subtract 75, divide by 325. We'll do it all real quick. Doesn't take long. What was that? Well, that'll be 75 divided by 325. So we got 0.2307, which needs to be e to that thing. So I'm going to do ln of 0.231 approximately, whatever that is. And then I'm going to divide by 0.324. Sorry I did that really quickly, but sorry, it was supposed to be negative 0.324. So 4.526. 4.526. Everything's in minutes? Yeah, T is in minutes. Okay. So it said The answer in minutes, it didn't say to round to anything in particular. But we'll just leave our answer that way. That'd be fine. But it's about 4.5 minutes, right? That's how long it takes. Which is not very long. Wow. It cools down quick. Seems unreasonable, actually. I think they should have picked a different K value. It seems unreasonable. I think pizza stays hotter longer than 4.5 minutes. Could be wrong. You're the one that asked, Delia. You look good? Okay. Again, emphasis on the fact that they will provide you with that formula if they give you this, and that was our mistake. We just copy and pasted this problem on here without really thinking about it. Let's return to this problem here. Check the time. Okay, we still have a couple minutes. Do you have another one you'd rather me emphasize? Eventually, I'll put the answer key here online today too. But. All right, the graph of the function g is the graph of the function f, but translated 2 units to the left. So that'd be log base 2 of, how do we work this? X plus 2. By the way, tomorrow's test is calculator active. So if you wanted to just like check yourself on a question like that, you could actually type in this and see that you did what was supposed to happen. The asymptote of the graph of the function h has the equation x equals 2. So maybe, will that do it? Yeah. Well, some of you have the log base feature under the math menu. You don't, well then you can just do the log of x plus 2 in y1 divided by the log of 2. And we haven't talked about why that works, but we're saving that for pre-cal. But I can just share with you that that's like a little thing you can do. I promise it works. The graph of a function p is the graph of log base 2 reflected across the x-axis. So how do we make that happen? How about that? Yeah? And what about this graph? Can we come up with the equation of that guy? Keep in mind that this is supposed to keep going down here like that. So it looks like it's been moved to the left 3. So I'm definitely interested in doing that. But that might be not, is that all? Didn't it? Isn't that a 1, 2, 3? Normally the asymptote, huh? Well, I mean, normally the asymptote's at x equals 0, but now the asymptote, don't you agree that the asymptote is at x equals -3?
Oh, yeah, you're right.
Yeah.
Sorry.
So I think it moved 3 units to the left. And is that it? The only thing I want to check on is 1, 2, 3, 4. I think the base of that log is maybe, is that 1, 2? Yeah, I think I like it. Yeah, that's good. I think I just checked a couple points and it seems to work. Okay, so. This is a fun problem, right? I squared is -1, I cubed is -I, and I to the 4th is 1. So what do you get? That's fun. How do we do? Oh, well, we didn't get to all of them, but there you go. We'll get some more later.